And I think we're in business. Over to you, Barry.
Okay,
You
the
might
mic
want
working?
to accept or reject something at the bottom.
I'll put this, which I think is reject. Thanks, Hugh, for the introduction. And hi, everyone. So yes, what an excellent introduction into AI we just had by Emmanuel, which makes my job much easier. So what I'm going to talk about today with regards to AI and machine learning is around neuroimaging in psychiatry. And we've had a lot of amazing talks, a lot of neuroimaging has been presented today. And there's been a lot of research in neuroimaging that has given us a lot of insights into mechanisms. But neuroimaging is not a clinical biomarker yet in psychiatry. And I'll try to explain why and why AI and machine learning can provide a solution to that. I'm going to use the example of clinical high risk in psychosis. So that's the area that I work. So I work with psychosis and depression, but it applies in other fields as well. So yeah, I don't think we need this because we had a lot of excellent examples of amazing studies that have been done with neuroimaging. But in clinical high risk for psychosis, for example, we had an amazing paper in 2003, a landmark paper, which showed that clinical high risk for psychosis patients have lower gray matter volume than healthy controls by Christos Pantelis. Macheri Kesavan in 2002 showed with his research in working memory and fMRI in fMRI tasks in clinical high risk subjects, again, these dysfunctions. We've seen that in task-based connectivity. We've also seen it in resting state connectivity. So over 20 years worth of work in neuroimaging, but still there's nothing in the clinic that can be used to diagnose or prognose or allocate patients to treatment. And why is this? I'll give another example. So this is a study that I've done with a colleague. So again, so here we've had some interesting results. So we find that clinical high-risk patients have less gray matter volume in these areas, really good p-value, less than 0.05 at the cluster level. Great, we can publish that. It's a statistical difference, but is it really a clinical difference between the patients? And that changes when you try and look at confidence intervals. So if you look here at the healthy controls and here the clinical high risks and here the measures of gray matter volume, you see there's a mean difference, and you get a nice statistical effect, a nice effect size, and you've got that difference between the two groups. But then if you look at the individual patients, you'll see that there's a lot of people with clinical high risk that are in the healthy control area, and you'll see that there's a lot of healthy control people that are in the clinical high risk area. And that presents its problems for clinical translation. So that's so problems with sensitivity and specificity, as it mentioned, yes. And this specific problem of sensitivity and specificity is really important for clinical translation. We need to have sensitive and specific tools if we want to see that clinical translation, if we want to see neuroimaging in this instance, but it applies in other measures as well if we want to see it translated into the clinic. And here I'll demonstrate a bit why there has been so little progress in neuroimaging in terms of clinical translation. This is a graph from a great paper where it discusses the problem of using neuroimaging as a biomarker in psychiatry. These are toy data, but if you think that the red line are patients and the blue line are healthy controls. So this is just an example of how positive predictive value and negative predictive value, look if there was a prevalence of what we're investigating of 25% and an effect size, a Cohen's d of 2, which according to the literature, an effect size of 2 is huge, it's a very good effect size. But you see that that translates to 0.64 positive predictive value and 0.93 negative predictive value. And in psychiatry, you don't have prevalence of 25%. And you can see here that the more the prevalence declines, then the more difficult it becomes to achieve these high positive predictive values in this example, and it applies also to negative predictive values. So when you have a prevalence of 1, so like in schizophrenia, we've got a prevalence of 1 to 3% in the population. In order to reach positive predictive values and negative predictive values of around 0.7, 0.8, you need effect sizes in classical statistics between 6 and 8. So we need to have that really, really significant statistical effect to do that. And the average effect sizes that we have here, I use the example of CHR subjects from healthy controls. The average effect sizes that we have from meta-analyses are 0.73, 0.1, 0.44, 0.63. It's good. Statistically, it's good, but it's not going to translate into the clinic. So that's where I think, and I hope I'll convince you, AI and machine learning comes. And it's also a bit of changing ways of thinking about psychiatry. So with the traditional statistics, you usually talk about schizophrenia recovery or depression recovery or anxiety recovery is associated with X, Y, Z. With machine learning and artificial intelligence, we can go using these complex algorithms that Emmanuel was talking about before. We are 80% sure that your family member will recover. So it changes a bit the paradigm and the thinking that we put into the research that we're doing. So I'm going to show you an example of a study that we did where we used neuroimaging to achieve something like this. A lot of speakers before have, I think, introduced this quite well. I'm going to talk about depression and psychosis today because that's, again, my interest. But we know that we've heard this today, that the current diagnoses that we have on the DSM and ICD-10 and 11 are built on experiential terms and symptom groupings. They have no relationship to underlying biology. And in my case, where I'm looking at brain structure, there's no link between the diagnosis and underlying neurobiology. So you'll get two patients who have the same diagnosis that might have different neurobiology. You might get two patients who have a different diagnosis but have the same neurobiology. And it is thought that this these problems contribute to, or one of the major reasons for this lack of biomedical translation in psychiatry, with their associated effects in disease and treatment course prediction. Now, specifically in depression and psychosis, they're really difficult to distinguish in early stages, so in the beginning stages of these disorders. And there's a lot of comorbidity of depression and psychosis. I think the numbers are something between, in psychosis, I think between 60 to 80% will have comorbid depression, and in depression, 20 to 30% will have comorbid psychotic symptoms, especially in the early stages. And in terms of the neurobiology, there's similar gray matter volume deficits in hippocampal and cerebral regions, and both have been found to be pro-inflammatory states with similar cytokines, IL-6, IL-8, C-reactive protein haven't been found to be elevated in both disorders. So in the study that I'm going to present, I wanted to take a bottom-up approach using neurobiological data across diagnosis, so depression and psychosis. And I wanted to see if we can have clusters that are based on neuroanatomical data from patients with recent onset depression and recent onset psychosis? And are they transdiagnostic, and do they perform better in predicting remission compared to traditional diagnostic categories? So to do that, we used the PRONEA sample, which, if you're not aware of the PRONEA sample, was led by Professor Nikolaos Koutsouleris, an EU-wide study. It had patients with recent onset psychosis, recent onset depression, clinical high risk, and healthy controls. And the really good thing about the study is that all these different samples were tested with the same questionnaires. So people with recent onset depression also got the PANS. People with psychosis also got the BDI and other measures. And to achieve our goals, we used, so Emmanuel previously talked about supervised machine learning. There's also unsupervised machine learning, where you don't tell the algorithm anything and it identifies clusters by itself. But we heard earlier today in the morning, I think, by Charles, about the dangers of that from the Drysdale papers of in depression, where if you use completely unsupervised machine learning approaches, the underlying, the algorithm might pick up on things that are not related to the disease, but more global effects. So semi-supervised machine learning sits between the two. It addresses some of those issues because it does use healthy controls in the process. So the semi-supervised aspect is that you tell the algorithm who are the healthy controls and who are the patients, and then the algorithm and then identifies clusters in the patient population. I'm not going to go into detail about the process, but if you have any questions, you can ask me later. But as a primer, it basically goes iteratively through a lot of different cluster solutions. So here we have one solution that separates healthy controls here in the blue and two patient clusters in red, then 3, then 4, 5, 6, 7, 8 iteratively, and then we calculate which solution is the most stable. And with that, we make sure that the heterogeneity that we're capturing is disease related, because each cluster is separate to each other, but it's also separate to healthy controls. So we used 577 participants from the PRONEA sample. So another good thing about the PRONEA sample is that we have a discovery sample and also a replication sample that's collected at a different time point that allows us to replicate whatever we find in the discovery sample. ROP, yeah, I see it here. It stands for recent onset psychosis. ROD stands for recent onset depression. These were people within the first 3 months of presenting symptoms and minimally medicated. We used whole brain measures derived from the computational anatomy toolbox from 280 regions. And then we repeated the same process in the replication sample. In terms of the analysis details, we use the repeated holdout cross-validation strategy. As I mentioned, we use 2 to 8 clustering solutions. Because the data came from a lot of different sites, and sometimes you might have side effects, we harmonize the data before we put them into the model. We used age, sex, and total intracranial volume as covariates of no interest in the model, so we regressed the variance of those variables in the modeling phase. We measured cluster stability. We did a clinical analysis of the clusters, a voxel-based morphometry analysis of the clusters. We tested the statistical significance of the clusters in 3 different ways. One, whether the signal that we got is different to what would have been found in healthy controls. 2, if the signal that we found is different to what, or same to what we would have found in other disorders and depression and psychosis. And 3, if the solution that we have is appropriate for, if the data that we have is appropriate for clustering, or if a continuous distribution would have been better. We then also tested the generalizability of the models in the replication sample. We then did a predictive analysis. So we had longitudinal data at 9 months, and we wanted to see if we could predict symptomatological remission. We're using baseline data at the 9-month point outcome. And then we also externally validated the data in 3 different completely external data sets. So I usually joke that we tortured the data to ensure that we have something stable here, and that's something that we can really analyze. So the solution was 2 clusters with a high ARI. So ARI takes values between -1 and 1. The clusters were transdiagnostic. There was no statistical significant effect of diagnosis. There was no statistical significant effect of sex or age. So there were no differences between the 2 clusters in those things. In terms of the clinical characteristics, we looked at that in 2 ways: in a univariate way using traditional statistics, and also multivariate way using machine learning. We termed the clusters preserved phenotype and impaired phenotype, and I hope it will make sense why we did that. So one cluster, the impaired phenotype, showed higher PANSS positive, negative, and general scores compared to the preserved phenotype. It showed negative symptoms as measured by the SANS, and it showed worse global functioning in role, current, and lifetime. The interesting thing, I think, is when we looked at the multivariate way. So we looked at the item level to look what are the things that are driving these 2 clusters. You can see that the BDI comes in both clusters, but there's a differential. There's a bit of a differential here. So for the impaired phenotype, it's changes in appetite and sleeping patterns. That's really important. For the preserved phenotype, more traditional, I'd say, typical depression, so loss of pleasure, guilty feelings, self-criticalness, irritability. Remember, these are clusters that contain both recent onset psychosis and recent onset depression patients. In terms of the PANSS, again, lots of difference here. Depression, the item of depression on the PANSS comes up on the preserved phenotype. Suspiciousness and persecution comes in the impaired phenotype. Again, a negative symptom differential. So allogia, grooming and hygiene, social inattentiveness and attention in the impaired phenotype, but anhedonia and asociality from the SANS in the preserved phenotype. And then in terms of the cytokines, there was elevated TNF alpha and elevated CRP in the impaired phenotype. And in terms of what was driving the difference in terms of gray matter volume, the impaired phenotype showed gray matter volume reductions compared to the preserved phenotype and across the brain, a lot of different areas that are usually associated with schizophrenia. But again, remember, these are recent onset patients across 2 different diagnoses. So we have the thalamus there, orbitofrontal areas, and as I mentioned, CRP and TNF alpha for the impaired phenotype and IL-1RA for the preserved phenotype. We externally validated, well, we replicated in the replication sample. I won't go into details that we did that well. It performed well in the replication. We also looked at 3 different data sets to see how they externally validated: the COBRA, MCIC, which are 2 schizophrenia data sets, and then the MUC, which is a depression data set. These samples are a bit older and have longer duration of illness. And the people who were assigned to the impaired cluster from these external data sets were usually the ones who had longer illness and a higher age, which means that in the clusters that we developed in recent onset samples, we might be capturing a signature of chronicity and poor outcome across 2 different diagnoses. And then I think the coolest thing about the analysis, which showed also some clinical promise, was when we looked at this 9-month outcome. So we used the GAF symptomatology remission because we wanted the transdiagnostic measure of symptomatology reduction. And we did these prediction models in the new the new neurobiologically based categories that we identified, and we also did it in the traditional diagnosis that we have. We combined inflammation data and baseline clinical data, and we show that the combination of these improve the performance. And yeah, the identified phenotypes perform, if you look at the balanced accuracy, perform on the area under the curve, perform much better and statistically significantly better than the traditional diagnoses that we have in predicting who is going to remit and who is not going to remit in 9 months. Do I have 2 or 3 minutes? Yeah. Okay. Cool. I'll quickly say. I just want to say that this an excellent PhD student of mine, Madalena Bushiman, is doing a similar process in using resting state fMRI. So we want to see if that is true also in resting state fMRI, and this is also including clinical high risk patients. She's finding some very interesting results, but I'm not going to be able to go into detail because we're running out of time. We're currently in the process of torturing the data, putting it into a lot of tests. So with that, I'll conclude. So we have, in this, we have 2 transdiagnostic clusters that are used based on neurobiological data, and the results are generalizable to the replication sample. And I think it's really interesting that the impaired phenotype, which we saw across 2 different diagnoses, was characterized by more symptom loading, functional impairment, gray matter volume loss, and elevated CRP and TNF alpha levels. The preserved phenotype had more central depressive symptoms and less impairment. And the impaired phenotype had widespread gray matter volume reductions in core areas. But I think the really important bit in this analysis is that these neurobiologically informed clusters outperformed traditional diagnoses in predicting remission. And just to finish in terms of the future directions, in terms of AI in psychiatry. We heard this morning an excellent speech about cancer and how they're looking at the different multi-omics levels. That's something that we really need in psychiatry, and Emmanuel also talked about before. We need a lot of data if we want to achieve these things. So we need well-characterized multi-site, multivariable data to do these AI and machine learning analyses that hopefully will produce solutions like the one I presented just now. Robust and novel AI methodology. So scrutinize, and this also leads with that point, the humility and ambition. So we need to have ambitious questions, but we also need to be humble. We need to scrutinize the solutions that we're identifying. Not just neurobiological data, but there's also other aspects, so environmental factors. And collaboration. I think I'll finish with that, and I see Hugh is stood up, so it's my cue to stop.
Thanks so much, Paris. Sorry for rattling us through, but we are getting a bit behind the clock.